Hello everyone. We are presenting Wallet, the confidential serverless computing. This work looks at a very important system problem, how to make serverless computing secure even when the underlying cloud infrastructure cannot be fully trusted. My name is Dev Trivedi and this presentation is based on the work wallet, and I'm presenting along with Akash and Zahid, and we are at NJIT. At a high level, the paper asks a simple but important question. Can we get the flexibility and efficiency of serverless computing while also getting strong confidentiality in cloud environments? And the answer proposed by system is yes, but only if we rethink how confidential execution is done. So, firstly, I would briefly walk you through the structure of presentation. So, here is the roadmap. We begin with introduction, where we explain why serverless computing has become popular, what security problems arise in that model, and why confidential virtual machines or CVMs look like a promising starting point. Then we move into key challenges. This is core motivation for the paper. Even though CVMs improve security, they are still not a good fit for serverless workloads because of several system level inefficiencies such as a large trusted computing base, slow boot times, high networking overheads, inefficient scheduling, poor consolidation, and expensive attestation. After that, the paper introduces Wallet, which is proposed system. Wallet redesigns confidential serverless execution around a much lighter execution model. Then the presentation covers Wallet's core components, its security model, and finally the evaluation results, where the authors show that Wallet improves both performance and security related efficiency in meaningful ways. With that roadmap in mind, let's start with rise of serverless computing itself. Serverless computing has become popular because it gives developers a very attractive abstraction. Instead of managing servers directly, developers write functions, deploy them, and let the cloud provider handle provisioning, scaling, and infrastructure management. That makes development faster and operations simpler. The slide also highlights the core characteristic of serverless paradigm. It is event driven, it uses function as a service, it scales automatically, and executions typically are short lived. Now, these benefits are real, but they come with an important trade off because functions are short lived, distributed, and managed by the provider. That makes security much harder to guarantee. So, the question is whether serverless is useful. It clearly is. Real question is how to secure it properly. The main security problem in serverless comes from the fact that execution is both ephemeral and distributed. Functions often do not run in isolation as one long application. Instead, they are chained together through network communication. Data moves from one function to another across multiple execution boundaries, often through infrastructure that user does not directly control. That creates several attack surfaces. First, there is data in transit. Since functions communicate over the network, sensitive information may be exposed to interception or tampering. Second, there is ephemeral nature of serverless. These functions live for very short time, which makes many traditional security techniques too heavy or too slow to apply per execution. Third, function chaining creates many handoff points. Every handoff is a potential place where confidentiality or integrity could break down. And finally, the underlying cloud itself may be untrusted. The provider infrastructure or parts of it may be compromised or malicious. The last point becomes especially important later because one of the biggest problem with existing solutions is that they trust too much software. A natural way to address this is confidential computing and specifically confidential virtual machines. Confidential virtual machines or CVMs are the starting point for this paper. A CVM provides a hardware backed secure execution environment for an entire virtual machine. One major advantage of CVMs is that they require minimal application changes. Existing workloads can often run without being rewritten from scratch, which makes adoption much easier. The slide lists several hardware technologies that support this model, including AMD SEVP, SNP, Intel TDX, ARM CCA. In general, CVM offers four important properties: memory execution, memory encryption, hardware isolation, remote attestation, integrity protection. Conceptually, the application still sits on top of guest OS, which runs over a hypervisor and then hardware. But now VM memory is hardware encrypted, so the provider cannot simply inspect it. To understand why, we need to look more closely at how CVMs actually behave in practice. This slide goes one level deeper into CVM's work and why overhead appears. On memory side, each CVM gets its own per VM encryption keys. That means one VM cannot directly access another VM's memory. The encryption and decryption are handled transparently by hardware, which is good for compatibility, but networking is complicated. When one CVM communicates with another, the data path is not cheap. The guest first encrypts the data and copies it into bounce buffer, then hypervisor transfers the data to destination CVM buffer. Then the destination copies and decrypts it again. So even though confidentiality is improved, communication becomes more expensive because of extra copies, extra transitions, and extra cryptographic work. The slide also introduces VMPL, which is layered privilege model. Where the VMPL 0 is highest privilege level and handles security, VMPL 1 is used for function execution in wallet, VMPL 2 is untrusted guest OS, and VMPL 3 is reserved. This matters because wallet later uses these privilege layers to create nested isolation inside a single confidential VM. That brings us to main problem statement of paper. This slide summarizes the central argument of paper. The author identifies six critical mismatches between standard CVM based designs. The first issue is large trusted computing base. CVM hosted serverless tech still include a lot of legacy software, around 4.8 million lines of code, which expands the attack surface. Second is slow boot time. It can take around 8.3 seconds to boot. The third one is high networking overhead. Because of bounce buffer, encryption, and context switching, latency becomes noticeably worse. The fourth is inefficient scheduling. A limited number of CVMs per node means more cold starts and higher latency. And fifth one is impractical consolidation. Since encrypted memory cannot be deduplicated easily, function density on each machine is limited. And the last one is high attestation overhead. Per CVM, attestation can take up to 1.1 seconds, which is extremely expensive for short-lived functions. So the problem is, how do we securely execute lightweight, short-lived functions in untrusted clouds while still meeting performance and scalability requirements? That is exact gap Wallet is trying to close. Now I'll walk through these issues one by one. The first issue is large trusted computing base. The slide compares the TCB sizes across different environments. Like in libOS is around 2054,000 line of code, and it increases gradually. A standard VM is larger and containers are still larger. The key takeaway is wallet achieves a 4.3 times trusted compute base reduction compared to CVMs. So insight here is that confidential computing alone is not enough. In other words, the paper is arguing that serverless needs not just confidentiality but lightweight confidentiality. Second issue is slow boot times. For serverless systems, startup time is critical. Many functions are invoked on demand and may execute only for short duration. So if environment itself takes too long to start, security ends up dominating the actual useful work. The paper identifies three major sources of CVM boot overhead. First is key generation, second is state initialization, third is attestation delays. All of this adds up to significant penalty. Even if we solve startup cost, there is still another problem: communication between functions. This part of presentation groups the remaining issues where first on networking overhead. The paper points out that distributed serverless application often rely on frequent communication between functions. In standard CVMs, communication is slowed down by strict isolation. The slide reports 9 to 20% higher latency than VMs. The next is inefficient scheduling. The platforms try to favor warm starts, but when number of CVM per node is limited, the scheduler is forced into cold starts. Then there is impractical consolidation because encrypted memory cannot be deduplicated effectively, and hardware limit caps the number of concurrent CVM. Function density stays low. Finally, there is attestation overhead. Full guest OS measurement can take up to 1.1 seconds, and in chained workflows, that overhead can repeat. Wallet swarm start attestation cuts this to about zero point 0.25 milliseconds through the differential attestation. That leads directly to the system proposed by the paper wallet. Wallet is presented as lightweight confidential computing system designed specifically for secure serverless deployment. The big idea is to stop treating each function like it needs a full heavyweight confidential VM around it. Instead, Wallet uses nested confidential execution and decoupled OS architecture so that each function can run inside a much smaller consolidation unit called trustlet. From a performance perspective, it lowers end-to-end latency by 93%. From here, Akash should take over.
Okay. Hello, everybody. My name is Akash, and I'm going to explain the architectural overview of Wallet. I would like to thank Dev for letting us know that what CVM is and what problem the paper wallet is trying to solve. And as Dev has listed certain issues, but before going on that, I would like to do a little architectural overview. All right. So we have seen the problems with Dev said with the CVM based serverless computing, and at a high level, Wallet ideally, let's go and see what Wallet is trying to do. So Wallet is trying to keep the security benefits of confidential machines, but remove the parts that make CVMs too heavy for serverless workloads. Ideally, we want to make it lighter such that it is easy, to run on the machines, which with the main idea being that instead of treating the entire guest VM as trusted, Wallet breaks CVM into smaller protection domains. Okay, so let's run through certain parts of it. Okay. And the first is the trusted. So there are like so there are four component parts in the hierarchy. We can see the trusted monitor, the trusted processes, data objects, and guest OS. Okay. So important component is trusted monitor, which runs at VMPL 0, which is the highest privilege level. The monitor is part of the trusted computing base, so it is intentionally kept small. Its job is to manage security critical tasks, memory management, attestation, and trusted process orchestration. Then we have the next level, which is VMPL1. Wallet runs it and it calls it trusted processes. There are two main types, zygotes and trustlets. A zygote is like a pre-initialized template for a function runtime, and a trustlet is actual isolated execution instance that runs as a serverless function. Okay, and then the next part. The next part is VMPL2, which is the guest OS. There are also data objects which are shared. Okay, and it actually means what it is written, like monitor, manage secure endpoints for interfunction communication, basically between the both of them, right? So the next part is the guest OS. The difference is that the guest OS is now considered untrusted. It can still help with orchestration, IO mediation, request forwarding, but it is or never will be allowed to directly access sensitive function data or trustlet memory. That was the entire idea which was said or which was introduced in the first part. Okay. Then data flow is also important. A user request is encrypted using function provider's public key. All right. The guest OS receives the request, but because the data is encrypted, the guest OS cannot read it. It simply forwards the request to a trusted monitor. Monitor now creates the input data object, as again, you can see where data objects lie. That's why I stressed on it, because it is shared. The monitor will then create an input data object and invoke the correct trustlet, and then the trustlet is going to execute the function, create an output object, and you know the response is returned. So that's the idea of this slide. Okay, can you move on to the next slide, please? All right. So let's talk about threat model and security boundaries. Okay. So since this paper is all about CVMs and how to properly use confidential sorry yeah how to use CVMs, the main idea is should also run regarding or around threat model and around security boundaries. All right, the slide explains that what is wallet defending against and what it assumes. Okay, so the most important, shift from the traditional CVMs, that wallet removes the guest OS from the trust boundary. Okay, and in normal CVM, the guest OS is usually trusted along with the application, but here wallet is assuming that the guest OS may be malicious or compromised, and basically assuming that giving guest OS any access is going to be problematic. Therefore, I need to do something. That's what wallet's idea is. Okay, so wallet considers three major adversaries. One is like the malicious guest OS. Since the guest OS runs inside CVM but outside trusted wallet components, it may try to steal user data, tamper with function execution, or access trusted memory, etc. Wallet defends against this using VMPL isolation and monitor controlled page tables. Then second is host to hypervisor. In confidential computing, we already assume that the cloud provider's infrastructure may be untrusted. So the host could try to inspect memory, manipulate IO, and do things like that. Therefore, wallet relies on the underlying CVM technology like AMD, SCV, SNP to protect against these. And the third is like the co-located malicious function. Since wallet tries to improve density by running many functions inside one CVM, one function may attempt to access another function's data. Wallet prevents this by putting each trustlet in isolated address space and only allowing communication through monitor managed data. So that's the idea behind all of that. All right. Okay. You also have to see at the trust assumptions, okay? Because it is really saying that I only trust the trusted monitor. So the entire idea here is that to trust something, create an entity of trust and then keep everything else untrusted, and then use something using which you take whatever new comes and validate it to the trust monitor and then let it run. So this is the entire idea. And security requirements as like encrypted protocols and TLS for communication, function providers to be trusted by users, and and also like things we also need to be careful about attacks like DOS, physical site, and side channel attacks and stuff like that. So yeah, so can we go to the next slide, please? One second. Where is this? Yeah, okay. Nested confidential execution. So I would like to take a little bit time with this. So this is a very important design principle. It is a nested confidential execution, which means what? The idea is inspired by systems like nested virtualization or ARM trust zone. Instead of having one large confidential VM where everything inside is trusted, we need to partition CVM into isolated execution regions. In this model, again, is the same thing, because we need to understand what is running at what VMPL level. Trusted monitor is going to run at the highest level. The trusted function processes run at VMPL 1, and the guest OS runs at VMPL 2. This is very important. Okay, so doing all of this, The guest OS is really isolated from the execution environment. This gives wallet three major benefits. First is the reduced TCB. Okay, sensitive code and data confined inside trustlets rather than being exposed to the full guest OS. Therefore, security vulnerabilities in the guest OS will not or never compromise. That is what I am trying to do. Second is better scalability. Okay, instead of launching one full CVM, wallet can run many trustlets inside single CVM. So that is like more aligned with the serverless idea. And third is fast communication. If two functions are co-located inside the same wallet environment and they are light, then they don't need to communicate through a full network stack. And that is the entire idea behind this. All right. Instead, they can use, monitor mediated shared memory objects. And this is like much faster than the traditional CVM networking, which was discussed in the first part. All right. And the implementation also relies on the hardware based enforced privilege partitioning. All right. All right. Okay. That is there. So that is the entire idea behind this. We need to understand, right? Uh, yeah, I think I've covered everything. Can you go to the next slide, please? Okay. Decoupled guest OS architecture. This might sound like I'm trying to repeat what was said before, but we need to look at it with a different idea. Okay, with a different design principle. Okay. In traditional CVMs, guest OS is part of trusted computing base. Here, I don't want to put it together. Okay, why? Because there it includes kernel code, driver system services, backward compatibilities, and everything. And all of that is a threat for me. Okay, second, if guest OS is compromised, then everything is compromised. Again, wallet solution is to separate the OS from the secure function execution environment. OS will still exist, but it will be 100% untrusted. Okay, this is something which I covered before. All right, but it is like similar in spirit to ARM's the trust zone secure world and normal world. Wallet has a secure side where the trust monitor and trustlets operate, and the untrusted side where the guest OS runs. The trusted monitor will initialize the secure environment and then isolate the guest OS from the function execution. All right, and yeah, all right, trusted. Okay, and the one key point which I want to cover is that wallet does not remove guest OS completely ever. It changes the guest OS's role. The OS becomes the helper, not a trusted authority, and that is the design principle that we need to focus in here. Can we go to the next slide, please? All right, so trusted processes, zygotes, and trustlets. So basically, I will call this like a worker processes of the main runners. That's what we can look at it as. So zygote is a pre-initialized template. It contains runtime environment. It needs to execute a serverless function. It's like Lambda functions in cloud, but not exactly. It's a they you know they are analogous, but not the same. All right, because zygote is a separate entity which was designed in order to run runtime securely. Instead of initializing that runtime from scratch, Wallet initializes it once and then reuses it as a template. All right. After initialization, the zygote's state is sealed and marked as non-writable. This means that it becomes an immutable base image. The trusted monitor verifies zygote, registered it, and then uses it to spawn actual execution instances. And a trustlet is an actual function execution instance derived from a zygote. So it's very important to know that when a function needs to run, Wallet creates a trustlet from matching zygote, and the process is fast because it uses copy on write. All right. Yeah, right. And then you can also have, it's a lightweight instance, and all the these things, the um, advantages are listed on this slide. All right, the copy on write mechanism is the real design principle here that has been highlighted in the slide that any write attempt to a non-writable zygote memory triggers page fault, monitor copies page, and updates the trustlet space table. Basically, trustlet is going to have high density of concurrent execution. That is it. Okay, can I go to the next slide, please? Okay, dynamically loaded libOS architecture. Okay, so dynamically loaded libOS architecture. Uh, so basically, the challenge is that here, one second. Yeah, yeah. So the challenge is that uh, wallet is dynamic. Is wallet dynamically loadable or not? Okay. So the challenge is that serverless platforms must support diverse workloads. One function may use Python, another may use Node.js, etc. Other ones. Traditional VMs-based systems often solve this by building full images, but that is too heavy for confidential serverless. Okay. On other hand, like unikernel style systems can be very fast, but they often require custom images and are less flexible for normal developers. So Wallet tries to get best of both worlds. It uses like lightweighted libOS runtimes and but loads them dynamically based on what the function needs and not in it. All right. A library operating system provides OS-like services required by the application. Instead of running the full general purpose kernel, it runs a smaller part of it. All right, like a system hardened part of it. Right. Uh, Correct. That is the wallet solution, and then you can see the idea is to have minimalist design and on-demand loading. The emphasis is more on on-demand loading because when I use a library OS, I don't want everything, but I only want what my requirements are and when I want it. So that's the entire idea, and you can see the flow through the trusted process tab. All right. All right. Can I go to the next slide, please? Uh, Yeah. Okay. So data-centric IO architecture. So data-centric IO architecture is the fifth design principle. This addresses one of the biggest performance problems in CVM-based serverless computing, which is the communication overhead. In traditional CVM networking, data mode was very expensive. So the guest encrypts the data and copies it into a bounds buffer. The hypervisor transfer it to the destination, and then the destination copies and decrypts it, and this creates multiple data copies, VM, exits, context switches, and etc. Okay, so what does wallet is doing? Okay, wallet's insight is that if functions can be co-located inside the same CVM, they should not need full network communication. Instead, wallet introduces data objects managed by the trusted monitor. Again, the entire idea here is that whatever wallet is going to use, okay, it's going to go through the trusted monitor. The network stack is did not be complete since the functions are co-located. As long as it is defined and it is approved by the trusted monitor, the problem should not be there. The entire idea which I said that before the CVMs used to have, before there used to be so many network stacks and stuff, that goes with this. And you can see at the data object workflow, and and you can see what why the performance gain is 27x, because everything is co-located, and that's the main part which we need to focus on. And I think next is going to be my last slide, and which is the differential attestation protocol. Right. So let's go over differential attestation protocol. And it is basically differential attestation is the principle. Attestation is essential in confidential computing. Basically, it tells me whatever I'm looking has been approved by somebody. Okay. It allows a remote user to verify that their code is running in the expected secure environment. But in serverless, the problem is that the functions are short-lived. If every invocation will require a full attestation of entire stack, the overlapped overhead will always be high. So how does Wallet solve this? Okay, so wallet solution is to avoid remeasuring everything on every invocation. Instead, it separates the system, which has been the trend throughout this paper, into immutable and mutable parts. Immutable parts are going to include the trusted monitor, the Zygote template, and the serverless function code, and they can be measured once, cached, and reused. After that, they are sealed and deployed. They should not change. The mutable parts are input and output. These are different for every invocation, so wallet measures them at runtime. Right, so this is the idea. This is the main idea in which wallet is going to function. And then you also have to look at the cumulative trust chain, which which has been mentioned here, because that is the pattern, that is the data flow, which basically implements the differential attestation protocol in wallet. And I think I'm done with my time, and I might have taken a little more, but I think Zahid is going to talk next. All right.
Hi, I am Sahib. Thank you, Akash and Dev. Uh, so I will start from Trusted Monitor. The Trusted Monitor is a core security component in the wallet system. It runs at the highest privilege level and is responsible for handling all the critical tasks such as memory management, attestation, and process control. It ensures that only trusted functions called trustlets are executed securely within the system. By centralizing these responsibilities, the monitor helps reduce the TCB, which improves overall system security. It also enforces a strict isolation between components and controls how data is accessed and shared. Overall, the trusted monitor acts as a secure control layer that maintains trust and protects the system from potential threats. Next slide, please. The trusted monitor also manages how different functions works together through function chaining, ensuring each step in a process is executed securely and is in the correct order. It controls how data flows between functions so that no unauthorized access or misuse occurs. Another key aspect is security governance, where the monitor enforces rules and policies across the entire system. This ensures consistent security decisions and prevents privilege misuse. At the same time, it considers performance impact, making sure that adding security checks does not significantly slows down the system. All right, next one, please. In this setup, the system assumes that parts like the guest OS, host, and hypervisors are untrusted, meaning they could be compromised. Because of this, sensitive operation cannot rely on them for security. There are also co-located functions where multiple functions run on the same machine. This increases the risk that one function could affect another if not properly isolated. To handle these risks, Trusted Monitor provides additional protections such as strict isolation and controlled access between components. It ensures that even if underlying system is not trusted, the critical operations remain secure. So overall, it protects system by not depending on potentially unsafe layers. Next slide, please. The trusted monitor works as the central security layer that controls and verifies all operations in the system. It also manages a secure communication protocol, ensuring that data exchange between components is protected and only accessible to authorized functions only. The system uses a libOS implementation which provides a lightweight operation environment for functions, helping them run efficiently without relying on a full operating system. Another important feature is copy on write handling, where data is only copied when modifications are needed. This improves memory efficiency and prevents unnecessary duplications. So together, these components help maintain a secure, efficient, and well-managed system environment. Next slide, please. The evaluation in experimental setup is based on a testbed configuration, which defines the system setup used for experiments, including hardware, software, and environment settings. This helps ensure that the results are consistent and reliable. The system also compares different baseline variants, meaning alternative setups or existing approaches used as reference points. By comparing these against these baselines, it becomes easier to show the benefits and improvements of the proposed system. Finally, the system is tested during various workloads, which represents real or simulated tasks. These workloads help measure how well the system performs under different conditions. Next control. This slide shows the performance improvements in terms of boot time and latency. The boot time comparison highlights the wallet starts functions much faster, efficient during cold start, making it more responsive than traditional CVM-based systems. It also shows strong end-to-end latency improvement, meaning the total time from request to response is significantly reduced. In real application, Wallet achieves up to 85 to 93% lower latency, which greatly improves user experience. So overall, the results demonstrate the wallet not only provides strong security, but also maintains fast execution, making it practical for real-time serverless workloads. Next slide, please. This slide presents performance results related to function density and networking efficiency. The paper shows that Wallet achieves extremely high function density by using memory sharing techniques, allowing many functions to run on a single node with minimal memory overhead. For inter-function communication, Wallet uses a data-centric shared memory approach instead of traditional TCP networking, which reduces communication overhead. As a result, communication latency is significantly lower, about 1.4x to 27x faster compared to CVMs. So overall, the key findings is that Wallet improves both scalability and communication efficiency, making it more suitable for complex serverless workloads, including function chaining. Next slide, please. Okay, in this slide, large-scale evaluation of system using Azure Functions Trace simulation, which reflects real-world serverless workloads. So simulation is based on traces containing thousands of functions and millions of invocations, allowing the researchers to study system behavior under realistic conditions. In the simulation setup, a multi-node cluster is used to process these workloads while measuring performance metrics such as latency. So the key results show a significant improvement in invocation latency compared to traditional approaches. The invocation latency CDF graph highlights that most functions requests are handled much faster with lower delays across both average and worst case scenarios. Overall, the result demonstrate that the system is efficient, scalable, and suitable for production level serverless environments. Next slide, please. So in this slide, it summarizes the main contribution of the system. First, it introduces a novel system called Wallet, designed for secure serverless computing in untrusted environments. It uses nested execution where functions run in isolated trustlets inside a secure environment, improving both security and efficiency. So the system also uses data-centric I/O, which also allows faster communication between functions by avoiding traditional networking overhead. Additionally, a differential attestation reduces verification time by reusing previous measurements, making the system much faster. So the security analysis confirms strong protection with a reduced attack surface, and the evaluation shows significant improvement in performance, latency, and resource usage. Last slide, please. So in this last slide, it presents Wallet as a practical solution for confidential serverless computing. So the key idea is to provide strong security while still maintain high performance. So Wallet achieves this by combining a lightweight design with secure execution using trusted components. So it significantly reduces the trusted computing base, which lowers the attack surface and improves overall security. At the same time, it delivers strong performance improvements such as faster startup time and lower latency. So Wallet also supports high scalability by allowing many functions to run efficiently on the same system. So overall, it demonstrates that secure serverless computing can be both practical and efficient, making it suitable for real-world cloud environments. So that's it from my side.